Good morning, everybody. I hope you're having a great day. Today is CodeForces round 712, which is also the divide by zero contest. I think this is like a pretty big thing in India, according to the contest. It's like very heavily advertised towards people from India. I am unfortunately not from India, so I can't win a t-shirt in it. But should be a fun contest anyway. We'll see. I forgot to register, so I'm a little bit late. And also, contest started like 2.5 minutes ago. So without further ado, we'll jump right into the problems. Here is problem A, array in peaks. A sequence of n integers is a permutation. It has all of those between 1 and n exactly once. Given two integers n and k, construct a permutation of n integers does exactly k peaks. Yeah, an index is a peak if it's between 1 and n. Okay, gotcha. So if it is not less than n over 2, it's impossible. Yeah, so you just take the, yeah, okay. So here's the idea. You can just take the original, uh-oh. My template still has my April Fool's prank on it. All right, very good. So you take the identity permutation. Is it multi-test case? It is, okay. Take the identity permutation. I plus 1, I guess. And then if k plus 1 times, or k times 2 plus 1, we'll use all of these indices. So, okay, if k is 1, we'll use indices 1 and 2. This is greater than or equal to n, and sys out whatever impossible is, minus 1, and continue. How many test cases? 100, sounds good. Otherwise, we just want to make all of these swaps. So for int I equals 0, I is less than k, I plus plus. So I1, like the first index, will be I plus 1 times 2, I times 2 plus 1. The second index will be I1 plus 1. All right, so then we want to swap these. One with 0 flips is 0. 5 with 2 flips. Flip this, 2 peaks, good. 6 with 6 flips is impossible. 2 with 1 flip is impossible. 6 with 1 flip, flip that. Looks good. That's problem A. Can't submit. All right, let's go on to problem B. A sequence of n non-negative integers for n greater than 2 is called good if for all I from 1 to n minus 1, the following condition is the case. The first n being true is equal to the last n being true. Okay. You're given an array of size n is greater than 2. Oh, it's called good if for all I from 1 to n minus 1. Okay. So for every I, the and of the prefix is equal to the and of the suffix. How many permutations does it work for? Oh, bitwise and. Okay, I was thinking booleans. Well, let's pause for a minute there and actually go back to booleans. Let's say it is boolean, so let's say we're just considering 1 bit. If we have something like this, 1 0 0 0 1 0 1. If we ever have a 1 followed by a bunch of zeros, like we have a 1 0, that's a problem. This breaks it. So you need to have a 0 in the beginning and a 0 in the end. Or you need to have all 1s. So, okay, so we look at the bits everything has. For the general case, we want to look at the bits every number has, because for each of those numbers, we can have them in every position. And this is just the and of all of the numbers, the and of the input. After we do that, we want to say one of those things has to be at the beginning, one of those has to be at the end, and everything else is free to choose. So that is n, or how many arrays or how many permutations? Permutations. Okay. So n, like n good, choose 2 times, so we pick the 2 that we want, the rest we can shuffle in any way, and minus 2 factorial is the answer. Good, so that should be pretty easy to implement. Let's check if it works for samples. This has 0 because there's nothing equal to that. Okay, so here 5 choose 2. 5 choices for the first, 4 for the second, divided by 2, so it's 10. Is that the case? No, 3 choose 2. You have 3 times 2 over 2, so there are 3 ways of doing it. Okay, so 3 times 3 factorial. 3 factorial is 6. 3 times 6 is 18. Oh, because it's not choose 2, it's choose 2 times 2. So it's n choose 2 times n minus 2 factorial. Gotcha. Yep, okay. Should be able to implement this in 15 seconds. Not quite, but pretty close. Alright, so we have each of these things. We have the count of the number of things that can be any n's, and then everything else doesn't matter because the n's going to be 0 for everything anyway. And we just need to say the answer will be count times long count minus 1. And then for int I equals n minus 2, I is greater than 0, minus. Ants equals ants times, or ant equals ants times I under mod. Good. Can we register? Oh, we can register. Nice. Maybe that was there the whole time. Oh well. Let's try submitting. Now, this contest is the divide by zero contest. And interestingly, the bot that is going to announce my verdicts on these problems is called Zero. So that's kind of a fun coincidence, which I enjoyed. We got A. Pretty confident we'll get B too. You're given an integer n. You have to apply m operations to it. In each operation, we got B as well. All right. You must replace every digit d of the number with a decimal representation of d plus 1. For example, 1912 becomes, so the first thing becomes 2, then 10, 2, 3. Okay. The length of n after applying m operations. So the length is just determined on the counts of each number. Yeah, it's a banger, super easy. So we just care how many of each number there are. Is m, uh-oh, never mind. Just kidding. Okay. So we have to do better because there are lots of test cases and lots of these digits. So the next observation is we can separate each of the digits out. So before we start, we can do a bunch of operations for each number and see how many of, we can do a bunch of operations for each number. We have company. We have company 0. All right. All right, cool. So, yeah, what was I saying? Okay, sorry, that was my bot, 0, and for some reason it was still listening, so I just turned it off, so it won't say the things or think the things I say to the camera are to it. Yeah, each digit we can separate. We can take 2 times 10 to the 5th steps for each digit, see how many digits that results in, and then add them up for each digit in the input. Pretty easy. Cool. Let's do it. So 10 digits, and we want to go that many steps. counts equals new int array 10, counts at start plus plus. So the answer will be a new int array of that size. Okay. Turn this at the end. Okay, so then we just call the simulation. Good. And now for each of these, we want to read in int n equals this, steps equals this. For char c in n plus this and char array, ants 0. The length, oh man, yeah, it probably does get huge. I didn't think about that. That's an easy thing to miss. But it is exponential, I guess. Technically it is. So if you take a lot of steps, it'll be gigantic. Alright, so int ants is 0. Sys out ants under mod. I guess let's make this a long so we don't have to mod a bunch. Alright, and then here we say ants plus equals counts at c minus the 0 character and this many steps. Good. Okay, should be fine there. So all we have left is this simulation method. Cool. For int step equals 0, steps less than steps, step plus plus. For I, okay, so I guess int sum equals 0, and I in counts, sum equals sum plus I under mod. And then ants its step equals sum. It's greater than or equal to the mod. Yeah, gotcha. Okay, so this just needs to be sum equals add sum I. It'll speed up computation a bit because this is probably slower than it needs to be. Okay, and now we need to go to the next step. Ants at 0 equals 1. I guess we can just start the steps at 1. Okay. So, up to 9, it behaves in an easy way. So new counts at I equals counts at I. Or new counts at I plus 1 equals counts at I. Then we have this issue for each 9. A 9 turns into both a 10 and a 1. So new counts at 0 equals add, or equals counts at 9. And then new counts at 1 equals add counts at 0. Sorry. New counts at 1 to new counts at 9, or to counts at 9. Because both zeros and nines contribute to ones, yeah. Okay, let's speed this up just a bit. Good. Then return it. I think we should be fine there. Oh, yeah, duh. Then new counts equals counts. Nope, vice versa. Counts equals new counts. Then we should be good. All right. This is under mod. This is under mod. And our mod, I think, is right. Good. Took probably way too long to implement. Should have been like a few minute problem, I think. But oh well. Yeah, not too bad. Wrong. TLE. Really? This, because I'm not using fast output? What is this? This is 100 times. This should probably be fast enough, I think. So fast. I am a fool. How did I break it? New counts, fill new counts with 0. Okay, it should still work, right? Does not still work. It must be this new counts thing. What was it before? Oh. Yeah, okay. So yeah, it's probably just print writer there. Anyway, GCD and MST. You're given some array of integers and an integer p. Construct an undirected but weighted graph of n vertices numbered 1 to n, in which the edges between vertices I and j are added in the following manner. The GCD of this range of the array is equal to the min. Then there's an edge of weight min of these things between I and j. If I plus 1 equals j, then there is an edge of weight p. What is p? Oh, the default value between I and j. The goal is to find the weight of the minimum spanning tree of this graph. Now, hang on a minute. Why is this edge weight 5? Oh, these are weight 10. Default one is 5. Gotcha. I see. So the GCD is always at least the minimum. And the GCD will change log times. Because every time the GCD changes, that means you remove a factor if you fix your starting point. So it seems like an easy problem, just maybe a little bit annoying to implement, but not too bad. So, sorry, I won't use paper. I'll use this so everyone can see what I'm thinking about. Here's the idea. We've got some array. Suppose we're interested in the edges this node has. We want to know when does the GCD change? So maybe here the GCD is like 15, and then here the GCD changes to 5, or I guess for this range it's equal to 5 maybe. And then for this range it's equal to 1. And maybe the minimum is 15 for these. And then here the minimum is 5. Or maybe it's 5 for this range. And then maybe the minimum is 1 for this range. So the edges we would add would be well, us to ourselves, but that's not helpful. Us to this, and then us to this. Okay, so now the next thing to notice is in each of these GCD ranges, we're going to add an edge to some suffix of each range. Right, once the minimum, yeah, once we hit the minimum, we'll keep adding to the end of the range. So, gotcha, yeah. So we keep adding the edge to the end of the range. So we can evaluate like which edges exist. But we have a minor issue here. And that issue is that we like it's kind of difficult to make this MST in this way because you might have a whole bunch of edges. So we need to be kind of smart with how we evaluate this. So we can say like for each L, we have a bunch of different ranges. We want to evaluate going in this direction. Yeah, that makes sense. So I think Prim's algorithm is where you have some set of nodes. You pick some starting node, and then you're going to make like a connected subtree. And you do that by finding the smallest node not in your group, and then unioning with that, like the closest node to one of these. So now you look at the outgoing edges from both of these, and then you union to that. You look at the outgoing edges from these, you go to that, and like to that, and then maybe to that or something. So if that were the case, then we can do this with a priority queue. Yeah. Yep. Okay. So what do we need to do this? We need... How much? Do we have a nice time limit? Not really. Ugh, gross. Okay, so extracting these is a bit tricky. I think we're gonna need range min. We're also gonna need range GCD. I guess this will be log squared for binary searching in RMQ for range GCD. It's gonna be tight, I can tell you that. All right, well, that's fine. We know how to do it anyway, so we should be fine. Okay. RMQ. We shouldn't need low memory for this, right? I think we should be fine. All right. Cool. So problem D. What do we need? We need an RMQ. This needs to be min, but we also need like an RGQ. We'll call it that for range GCD query. Is everything an int? Yeah, good. All right, so this is GCD. This also needs to be the GCD. right, so we have both of these. Good. Okay, multiple test cases. We want to read in N and P. So we'll have some node, maybe. Maybe one int ID. We probably also want like a bunch of ranges. Okay, so let's make this static, I guess. This integer p. What now? Oh, this is going to be a bit messy. So we need to say, in this range, is there anyone who is currently not included? This is disgusting. Okay. Static tree set of integer nodes not included. There's new tree set integer. Okay. All right, so that's static. For I equals 1 less than n plus plus nodes not included. That add I. All right, cool. Actually, this is a good data structures problem. I like it. Yeah. So each node needs a bunch of ranges. So make a range class range. Int from, int to, and then int cost. All right, cool. So we have this. Yeah. All right, gotcha. So we want a priority queue of ranges that we can pick. Probably also want the node who's the owner. No, I guess it doesn't matter. Right? Okay. So we need a priority queue. Of all of the ranges we have. Gotcha. All right. So what now? We need a getRanges method. Do we want to add all of the ranges immediately to the priority queue? Probably, doesn't hurt. What are we going to need for this? We're going to need an RMQ, minQ, and an RGQ, GCDQ, or GCD, RMQ. Okay, so this will get us a bunch of ranges for this node. And we need to do some unioning here. So ranges.add nodes at 0. Oh, we need a node array. Cool. So what else do we need here? So we need to build, we need to build this range. We need to fill it with like the ranges from node 1. So nodes at 0 dot get ranges. Okay, so we need these now. So rmq min rmq equals new rmq a. And we also need GCD, this is an RGQ, standing for range GCD query. Should probably just have this add them. Okay, get ranges, this to this. Pass in ranges. Good, all right, cool. So, well, not, nodes not included dot is empty. Well, there are more nodes not in our current connected component. Range next range equals ranges dot peak. Okay. If nodes not included dot floor next range dot. Wait, what do we want here? Do we want to connect to the, we probably want to connect to the first of them. Yeah, because all of these edges are bidirectional. Ceiling next range okay, I guess maybe these do need to be bidirectional. Yeah, for Prim's algorithms to work, they should probably be bidirectional, so it doesn't matter. Ceiling this is less than, okay, so int can equals nodes included dot ceiling next range dot from. So if this is actually in the range, if it's less than or equal to the 2, then actually add it. Then nodes not included dot remove canned. Otherwise there's nothing we can take, so this range is useless, so ranges dot remove. Okay, so remove it. Long cost equals 0. If next range dot cost is greater than p, continue. well, I guess just throw null. We should never reach that. Okay, so remove this candidate node. Cost plus equals this canned, or cost plus equals next range dot cost. What else do we need to do? We need to add everything this new guy has. Ranges dot add, or ranges dot, sorry. We need to do the new guy, nodes a canned dot get ranges. Cool, we'll keep doing this till we're done. Then this will be empty eventually, hopefully, and then we print the cost. So all that's left is this. Okay, so first, binary search all times the range changes. Then for each of those times, binary search when the GCD works. Uh-oh, we have a problem here. This runtime is going to be log cubed. Yikes, because we're doing a binary search for each of the times it changes, and each of those we're doing GCD checks. It's very messy. Well, I don't know how to fix it. New range from -1, or I guess from ID -1 to ID +1. What is the cost? Cost would be P. Yeah. Okay, next thing, we can add to a bunch of ranges in both directions. Okay, so if GCD, or if GCD RMQ query, no, it is just log squared. Good, okay. If query from ID to L equal to GCD RMQ query from ID to n-1. Okay, so static int get range. We need the GCD RMQ. We need the L. If we have both of those, we need to get the range. right end of the GCD range. Okay. In log squared. Yeah, so it's a little messy, but hopefully it should be fine. Okay, so we'll binary search this time. So go from, if this is the case, then we're done. Okay. Yeah, so if L equals N, we break. Otherwise, int R equals get range R, RGQ, GCD, RMQ. And then pass an L, and then at the end, L equals R plus 1. RGQ, GCD, RMQ. Nope, what am I saying? Thank you, okay. So we get the L, we have the R. If R min RMQ query from ID to R is not equal to int target GCD equals GCD RMQ.query from ID to the right end of the range. Okay, so if the GCD across the range is not equal to the target, is not equal to the min, if that's the case, then this is not possible. Okay, so otherwise we want min split would be L, max split would be R. While min split is not equal to max split, int mid equals min split plus max split over 2. All right. Query from ID to mid, it's equal to this. That means it's possible. What do we do if it's possible? We make the range bigger. So we say max split equals mid. Otherwise, min split equals mid plus 1. Yes. We want to round down, one convenient. Okay, in this case, we want to say add2.add. What do we add? A new range. Oh, we only want to do this. Okay, so if, or I guess target GCD is greater than P. Then we continue. Cool, so we have all of this stuff. In this case, we want to add to the add2 list. Add new range. Range goes, where does this, what do we do here? So from min split to the right end of this range. We want to add something with cost target GCD. This is crazy complicated. Okay, so much stuff going on. Good. All right, so we've got this range added. Now we need to do this. We also need the reverse. We get range L. Okay. R equals L. R is equal to -1, then break. Otherwise, L is equal to get range L, pass in the R. GCD query from L to ID. That's what we're looking for. Should be L to ID. It's not equal to the target GCD, or the target GCD is too big. In this case, R equals L minus 1. Okay. Min split equals L, max split equals R. Seems right. Query from mid to ID, if it's equal to the target GCD. It's possible. Then max split equals mid. Otherwise, min split equals mid minus 1. Yeah, so if this is not possible, okay, if it's possible, we move it up to here. We want to find the last time it's possible, so move the max up to here. If it's not possible, I guess we move the min up to this. Is this right for the other one? Okay, we want to find the last time it's possible. If it's possible, oh no, so this is a prefix. So it's a prefix, so we want to find the first time it's possible. If it is possible, we move the min split up to this. If it's possible, if the, okay, so it's a suffix. No, it's a prefix here. It's a prefix. We want to find the first time it's possible. So if it is possible at this position, we want to move the left up to the mid. Otherwise, we want to move the max up to mid minus 1. Yep, okay, and then we do +1 because we want to round up. Okay, almost there. Okay, so get range R. Int target GCD will be GCD rmq.query from ID to L. Not static. Query from ID to L. Then we want to see how much longer this is the case. So int min would be L, max is n minus 1. So if we query from ID to the mid, this is equal to target GCD. This is the case. Then min equals mid. It's not the case. Max equals mid minus 1. Okay. This case we query from, this is an R, or from the ID to the R, or from R is on the right side to the ID. Yep, that's the target. The min is 0. The max is R. Sounds like the mid. Okay, query from mid to ID to the target GCD. This is the target GCD, then max equals mid, otherwise min equals mid plus 1. If it's not, yeah, don't go this far. Turn mid. Good, I think we're good. Nope, this is wrong. Is this also wrong? Have I not changed this? Okay. What's going on here? So I fixed the binary search. I need to modify this still. Add a range. So we add a range from it's going to be a prefix. So from L to min split. Target GCD, and then in this case R equals L minus 1. I think we're done. Took a very long time to implement, but crashes. Who saw that one coming? Okay, 4 test cases, 2, 5. Let's just sit with this for a moment. Query. Oh. Yeah, this is wrong. This ID, what is ID used for? It's just the index everywhere, I think. We're never actually interested in the value. So this should be just I think. Oh boy, how many for loops could this be stuck in? How many binary searches could we be in here? Oh, so many. Okay, all right. Okay, we're infinitely in E. 0, 1. Yeah, it should be +1. And this should be, yeah, what it is. Okay, next crash. 31. Query. So R is 2. R is 2. R equals not L, R equals ND. The answer to that 5? It is. Oh my goodness. Lucky me. Does our luck stick? Five, 3, 12, 46. Oh my goodness. Submit. Man, people did that pretty fast. Oh, am I in a TLE? Runtime error. Runtime error. What does that mean? All right, let's come up with some tests. What might crash us? 1. Say we have 10 things. GCD is 100, or the default's 100. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 9. Yep, okay. Yeah. P and N gets set here. I wonder if it's this. Okay, what would be required to randomly generate this? We need n, p, and then an array. Just this. Okay, we can do that. Static final random. Bounds on n up to, or at least 2. Oh, gotcha. Ugh, that was annoying. Nice. All right, problem E. An array is called beautiful. Man, so we're getting crushed by some friends here, right? Yeah, nice job. Colin, geothermal, nice job on E. Good job, good job. An array is called beautiful if all of the elements in the array are equal. You can transform an array using the following steps any number of times. Choose 2 indices and some integer. Let the first, okay, let this be the source and this be the sink. Decrease the element in x, decrease the ith element by x, increase the jth by x. The resulting values at the I and jth index are these. The cost of this operation is x times the difference. Note the ith index can no longer be the sink, and the jth index can no longer be the source. The total cost of the transformation is the sum of all costs in step 3. Array is called balanced if it can be transformed into a beautiful array, and the cost of such transformation is uniquely defined. In other words, the maximum cost of the transformation equals the minimum cost. Your task is defined the number of balanced arrays, which are permutations of the given array. Gotcha. Okay, so we want to make everything equal. So first of all, the sum of the elements needs to be, like, we know what everything needs to be. Okay, let's say everything needs to be 0. Like, set everything to 0. And then we're going to say we're going to decrease from everything so that we can. All right, so you've got a 3, and then something that it matches with. What if you do 3, -1, -2? So you could do this here. If you did this, this would be, so then you do 0 to, okay, the sum of the array needs to be 0. in the beginning. So this goes to 0. This goes to minus 3 plus 3, so this is plus 2. And then afterwards, this goes to 0. This also goes to 0. So what's the cost of that? We transfer 3 here. So 3 times 1 plus 2 times 1. Okay. Alternatively, if you have 3 minus 1 minus 2, you could do this. This would be 3. Here, so this is 0, this is plus 1. Then you can do 1 here. Now this is 0 and this is 0. So it's 3 times 2 plus 1 times 1. This is equal to 7. This is equal to 5. So this is not legal if they're ordered like this. Yeah, okay, so like, it's always possible. You can just push something over and then push it over one more time. You can do 3, then you can do, like, so you need to push 3 over, so this needs to be 3, this needs to be this prefix sum. At the end, the prefix sum needs to be 0. Can you do better? Probably not. Right, that's how much needs to be pushed over. Beyond that, you could maybe push so what is some that would work? 1, 2, 3. You're saying any permutation works? Oh, I can't be the sink anymore, but it can be the source. Gotcha. I slightly misread the problem then. All right, I'll be right back. Need some calories in my brain in order to think about this. Yeah, okay. So the idea is pretty easy, I think. Like, everything that's positive, you have to take from it in order to make it 0. So each of these things, this needs to be the source, and these need to be the sink, and that's it. So like naively, what you would do is you would just take this thing, and then like the best you can do is take the first of these, give it to the first matching thing, and just keep doing that. Like first ball goes in the first hole, second ball goes in the second hole, third ball goes in the third hole. That's pretty easy to calculate for some permutation. But I suspect if you have 2 balls with 2 holes, you could do this, right? That would be a problem, because that would have a cost of 4 when you're looking for a cost of 2. So why is it that this has an answer that isn't 0? Oh, yeah, that's interesting. 0, 0. Okay, so if you have plus, you have all the positive elements here and all the negative elements. That's easy. Yeah. Is there any other case? If you have one positive element, okay, so you have one positive element, it can go anywhere. If you have one negative element, it can go anywhere. So this is n factorial. 1 plus or 1 minus is n factorial. Otherwise, you have to split them like this. Positives and the negatives. You can also do the negatives and then the positives. Yeah, okay. Pretty sure that's it. That's like the only way of doing it. All right. Now we need to worry about duplicates. It's kind of annoying. Okay, so how many permutations of some array are there? N factorial over size factorials. Right, because we can orient any of them however we want. First one, there are this many ways to rearrange it. They're all the same. This way, there are this many ways to rearrange it. Yeah. Okay, so this is what we divide out. So that's like how to split it into different groups. Is there any other parts of the problem we're missing? This, one test case. Sounds good. Let's do it. It's way easier than D. Okay, and then we need to pre-comp, so static long array facts, static long array facts inverses, new long array will do 10 to the 6, I guess. Wait, how big do these numbers get? 10 to the 5th should probably be fine. 2 times 10 to the 5th. Fact inverses static void pre-comp. I'm going to call our pre-comp up here. Facts at 0 equals 1. Okay, cool. So we can pre-comp stuff. Yeah, what do we need to do here? So we need the array, one test case. Read array says n. Long sum equals 0. Add that to the sum. So if sum mod n is not equal to 0, then we have a problem. Then it's impossible. Good. Okay, so cool. So what can we do? So int positive count equals 0, neg count equals 0. For I and I is greater than 0, positive count is plus, else if less than 0, then negative count plus plus. Alright, so if positive count equals 1, or negative count is equal to 1, then the answer is n factorial. Facts at n. Okay, otherwise, positives all need to be on one side. Cool. Oh, the zeros can be anywhere. True, okay. Yeah. Yeah, okay, so, well, this is, the 0 thing is just going to be n choose k. Okay, so what is this going to be? Long ways equals 0. Ways equals multiply ways by n choose k. There are n things. We want to pick this many to be zeros. And then sys out ways equals multiply ways by 2. All right, ways. Yeah, so we need all the positives on the left, all the negatives on the right. How do we do that? How many? Okay, so it's a bit tricky. Because we need a hash map of how many times we have everything. I, default to 0 plus 1, put that into I. Okay, cool. So for map.entry integer to integer e in counts of get entries entry set. So positive ways will initially be factorial of positive count. This will be facts of negative count. Positive ways equals multiply positive ways. Okay, so oops, if e.getKey is greater than 0, else if e.getKey is less than 0, positive 0, then we subtract from positive ways. So positive ways equals multiply positive ways by fact inverse at e.getValue. Otherwise, we do the same for negative ways. Good. That's annoying. Why is that? No, not the case. This is also not the case. That's just blatantly wrong. Okay. We have nothing positive and nothing negative. The answer is 1. Always, okay. We have some positives and some negatives. Yeah, okay, so now long ways equals facts to n for this thing. Ways equals multiply ways fact inverses at e dot get value. Say we have 10 things. Should be 2 ways of doing it. Good. Say we have 6 things. We've got a 5 minus 1, 2, 3, 4, 5. Yeah, it's better. Lots of wrong answers. Sloppy contest. Wrong answer, test 2. Wrong answer, test 2. Wrong answer, test 4. This might be wrong. Maybe not. Okay, you got it. Is set realistically solvable? Geothermal did it. What's the last problem? Swapping problem. All right, you're given 2 arrays A and B, both of size n. You want to swap 2 elements in B at most once. You want to minimize the value of the sum of the differences. It doesn't seem that hard. Yeah, so swapping one pair in B is the same as swapping one pair in A. So we'll just run our code twice. And we definitely want, like, we might as well just not swap if the B values are bigger in both cases. Yeah. So we want like B to be bigger than A and then A to be bigger than B. And we want to swap them. So we want B or B1 to be bigger than A1. If B2 is bigger than, yeah, okay, then we want like A2, B2. There aren't that many ways, okay, of untangling this. You've got something like, so you have, let's say A1 always comes first. This is the biggest. This is, I guess, the smallest. So A1, okay, there are some other things. So you can have A2, B1, B2. You can have A1, B1, A2, B2. You have A1, A2, B2, B1. But in both of these cases, if you swap the two B's, it doesn't change anything. So these are useless. Okay, A1, B1, A2, B2. A1, B1. I guess let's just try to like swap these. So A1, B2, A2, B1. And then you also have the one where A2 is last. So you have A1, B1, B2, A2, and then A1 with an A2 at the end, and then B2, B1. So here are your two interesting cases, this and this. Here, if you swap two, it doesn't change your total cost. B1. So in this case, you pay for this and this rather than this and this. So this is always desirable. And in this case, you pay for this and this instead of this and this. So this is always desirable. So there are two things you look for, either A, B, A1, B1, then an A2, and then a B2. And the gap you get, the amount you get, or wait, we're looking for this here, or for this here. So A1, B2, followed by an A2 and B1. And then we want this gap to be as large as possible. We want B2 minus A2 to be as big as possible. Mo's? Maybe. What's the other one? The other one is, I guess we don't have time to implement it, but A1, so that is A2, B2, A2, B1. We also have A1, B2, B1, A2. and you want this gap to be as large as possible again. Yeah, it looks like a sweep. Looks like you can do a sweep with like a segment tree or something. Probably not too bad. We don't have time to finish it though. Okay, yeah, so I guess the real question is Colin got it. Nice job, Colin. Good job, good job. Yeah, if I had another 15 minutes, probably. But, oh well. I guess let's go over solutions to the ones I've solved. What case undo here? Got sick of it. Fair enough, I guess. Yeah, we'll go over solutions here to A through E. And then a general idea for F, I guess. Sounds fair enough. So problem A, arrays and peaks. So you want to make some permutation of the numbers from 1 to n, which has exactly k peaks, and a peak is where it goes up and then comes down. In order to do that, what you can imagine doing is if you have the numbers from 1 to n like this, if you swap these two elements here, you can create a peak. You can create a peak for free. And then this stuff is all in the same order as it was before. So all of these things are still bigger than everything before you, and they're all still in the same order, and you've created your peak. So that's a really good way of doing it. You can just take two elements and flip them. That creates a peak, and it uses two elements. That's as compressed as you can do it as possible. And if you do that, you can solve the construction that they're looking for. So the code for that is pretty simple. First, to check if it's impossible. If it's not impossible, you do k-swaps, where the swaps go from I times 2 plus 1 to whatever that is, plus 1 more. And yeah, you'll get something that looks like this. Like you'll get like a bunch of these like saw edges sort of thing, and then after that it'll just increase like that. So yeah, cool. That should work. That's problem A. Problem B, forgot what the problem was. And sequences. Oh, this was a cool problem. I liked it. This was really interesting. You've got an array of integers, and you want to have it so that the and of any prefix is equal to the and of the opposing suffix. So the and of the first three elements is equal to the and of everything but the first three elements. And the and of the first one element is equal to everything but the and of the first one element. We can look at this for a minute and get some good information here. So let's say that the array looks like this. So we've got some elements here. We don't know what they are. The most interesting case to look at is just what happens right in the beginning. So right in the beginning we have this here, and then like just the first element on one side, everything but the first element on the other. In this case, if there are any zeros in this suffix, that means the first element has to be a 0, right? Let's look at it just for like just one bit at the moment, rather than for all the bits. But if there are any zeros in the entire suffix for this one bit, that means the prefix has to have a 0 in this bit. And if this has a 0 in the bit, that means that when we look at this range here, everything but the last element, that means the last element has to be a 0. So, because this is a 0 here, which means the end of this part's going to be 0, so the last element's going to be 0. So if there are any zeros in the entire array, both the first and the last element need to be a 0. If there are no zeros in the array, well, I guess it doesn't really matter, right? If it's always going to be a 1, the end of anything is going to be a 1. If the first and the last elements are zeros, it doesn't matter where you split it, because anywhere, if you're looking at a prefix and a suffix, the end of both of them are going to be 0. So that's the extent of the requirement. For each bit, if either everything's all ones or both the first and the last thing in the array are zeros. Now, we can check the bits that everything's all 1 for pretty easily. If we have like some numbers in binary like this, the bits where everything is all 1 is just the cumulative AND of all of these numbers. So the AND is going to be this, which is equal to 2 in binary. So we take the AND of all of the numbers, and the AND of all of the numbers is what has to be in the first position and the last position. Everything else can be whatever we want. So there's a little bit of combinatorics there. Basically, if like you have 10 numbers, and then 3 of them can be in the first or the last, you have 3 choose 2. That's how many ways you can pick the first and the last element. You can swap the 2 if you want, so times 2. And then you have 8 other elements, which you can do whatever order you want. So there are 8 factorial ways of doing the rest of the elements. And this is your final answer. Yeah, so that's kind of somewhat basic combinatorics, a little bit of counting, but not too bad. All right, on to problem C, add 1. So you have some integer n, and you want to apply m operations. In each operation, you take each digit, add 1 to the digit, and then concatenate everything together. So for 1912, for instance, the 1 becomes a 2, the 9 becomes the digits 1 and then 0. So the length of this number gets 1 longer. The 1 here becomes a 2, and this 2 becomes a 3. So you get the number 21023, because the 9 becomes a 10. The thing you have to figure out is how long is this, how many digits are going to be in this number after you do m operations. And the idea here is if you're going to do m operations, all you care about is the length of the number. You don't care what the number actually is. And since each of these digits are like separate, you can separate the digits out in the beginning. So all that matters is how many of each digit there are, not what this number looks like. Importantly, like one tricky part here is you have a bunch of test cases, and then you also have a bunch of steps in each test case. So yeah, it's a bit tricky. It turns out you can actually do this with matrix expo. So if you know matrix exponentiation, I'm pretty sure you can use that to solve this in log time per test case. So if m was like up to 3 times 10 to the 9, or up to 10 to the 18 even, I'm pretty sure you could still probably solve it. But it's not, doesn't make the problem too much more interesting, I think. So I like it how it is. Awesome. So what do you actually do for this? Well, if you know like the number of 1s, the number of 2s, the number of 3s, etc., what you can say is each 1, if you look at the 1, what is the 1 going to turn into after this many steps? So if you take k steps, you start with a 1, how many of each number do you wind up with? And you can look at how many of each number do you wind up with, or I guess more easily, how many numbers are there total? But in order to do the calculation, you have to say, okay, after 1 step, which numbers do I have? After 2 steps, which numbers do I have, etc. So yeah, that's the idea. You're going to say for each starting digit from 0 through 9, if you start with one of those digits, how many digits will there be at the end? How many digits does this thing turn into? And that's something you can do, because if you have this 0 and you have like some other digits over here and over here, this 0 might expand to more stuff like this. But these things will always stay before it, and they might expand too, right? But everything stays, once it's separated, it stays separated. So you can just count them individually. Kind of looks like a volcano. It is important to notice that this grows exponentially, so you do have to remember to use mod, and they tell you to use a mod anyway. The reason it grows exponentially is every 10 steps, you increase your number of source nodes, right? So if you imagine taking 10 steps at a time, it'll double every 10 steps. So after 600 steps, it's doubled 60 times. So you've multiplied it by 10 to the 18. It's very big. Okay. Here we go. GCD and MST. This problem, I thought this was a pretty hard problem, actually. Maybe I overcomplicated it. I thought it was just kind of difficult. So the problem is you're given some array. You want to find the MST of a graph that you can use this array to build. Of course, if you actually build this graph, it'll be way too big. So you have to use observations about the process of what you would use to build the graph so that you don't have to build the entire graph. You can only look at the interesting parts of the graph and from there get the solution. So yeah, what is the process? Well, first of all, you start with adding edges between every adjacent node. So you put all the nodes in a line. Every 2 adjacent nodes, you add an edge of weight p. And then after that, you add these additional special edges. And these special edges are kind of cool. So if the range of some GCD is also equal to the minimum along those elements in the array, then you add a second edge. Cool, that's the problem. How do you do it? Well, this relies on, I guess, one common fact, one crazy trick, which you really need to know. And that trick is, suppose you start at some index in the array. If you take the GCD as you go to the right, the GCD might change, right? So if you have the numbers like 12, and then you have 18, and then you have 6, and then 12 maybe, and then you have 9, 27, 15, or that's a bad example, let's say 5, and then 7, right? So let's say we start at this number and we take the cumulative GCD. Initially it's 12. And then after we see this 18, the GCD will decrease to 6, 6, 6. When we see this 9, decreases to 3, stays 3, and then it's 1 from this point. So the thing to notice here, let's look at these continuous blocks where the GCD is all the same. And then it'll be 1 forever on here. What we can notice is between these blocks, what happens is the GCD loses 1 or more prime factors. In this case, we just lost a 2. In this case, we lost another 2, and in this case, we lost a 3. You might lose more than 1 prime factor between blocks. But each block, you lose a prime factor. So if this happens every time you move from one block to another, that means every time you go across a block, you lose a factor. So you can only have a logarithmic number of blocks here, which means the GCD can only change log times as you go to the right. So there's that trick. It's a pretty common trick. We can use that to say, okay, let's split this array up into blocks for each starting point. You go for blocks both on the right and on the left. And then we want to say, okay, for this block, this one block here, let's say the 6s, we want to see for what range of elements here, for which elements from here to this, from like the 12 to the end, for which ranges is the minimum along this range going to be a 6? Well, what we can notice first of all is the minimum is never going to be less than 6. Because if there's any number less than 6, the GCD will be less than 6 as well. So we know the minimum in any of these ranges is 6 or more. We want to see when is it equal to exactly 6. So what we can notice is either it won't be equal to exactly 6 at all, which is possible, right? If we had like 18, 12, 12, the minimum is never 6, but we do have a 6 here. Or if we have at least one 6 in this range, or before this range, we want to say it's going to be, the GCD will be equal to the minimum for some suffix of this range. So in this case, for this suffix, we're going to have edges from the 12 to every node in this range. We can for this, if we know this blue range, we can calculate what this red range is in log n time by binary searching in RMQ. Okay, there's a lot of stuff there. Binary search, hopefully you're familiar with. If you're not familiar with range minimum queries, RMQ, put a lot of effort into explaining them in an algorithms thread video that I made. So you can look at that. I explain how RMQs work and why you should use them. And yeah, it's in the algorithms thread series. So, but basically the idea is you can binary search on the RMQ to find when, the minimum here is going to be a 6. You can binary search when the first time the minimum is 6, because the minimum is going to be decreasing. You find the first time it hits 6. Okay, so you know that. So we can find the range here of things we add edges to. Now we're going to add edges to all of these things, and the cost will be 6. Right, so we add an edge here that's 6, and an edge here that's a 6. Okay, so we have this range that we add edges to, but we have log n versions of this range. So this range is one example, but we might have some example here where they're like 3s. In this case, we don't. Some example here where the minimum is 1. In this case, we don't again, but maybe if we add a 1 here, if we add like 2 more numbers, a 1 and then a 5. We also have, let me move this so my face isn't in the way. We would also have this range right here, okay, where these edges are of cost 1. So we'd add 12 to this is cost 1, 12 to this is cost 1. And yeah, so we have all of these ranges of edges which we add to the graph. Now, if we're looking at ranges, there are n log n ranges of these edges, but each range can be pretty big. So in total, there can be n squared edges. The example for that is really easy. It's just an array that's all the same element. So we can't actually build every edge. But if we look at the ranges, we can do some stuff. We can use some data structures, either like a set or a tree set. And then we can optimize that to make it go very fast. We only look at a logarithmic number of edges for each edge that we end up taking. Okay, so what's the idea? So now we have like some way of seeing edges that are interesting. What we're going to do is use Prim's algorithm. So we have a bunch of nodes in the graph. We're going to pick some starting node, and then we're going to say, okay, we want the smallest edge from this node to any other node in the graph. What you can look at is see that you have a bunch of ranges here. So let's clean these up a bit. We don't look at these individual edges anymore. We have a bunch of ranges. This range is going to have cost 6. This range is going to have cost 1. We want whatever range has the smallest cost. So this edge here has cost 1. We're going to say, okay, the edges this can reach are these consecutive edges. We want to see, are any of these edges things we don't already have as part of this group? And yeah, okay, this one isn't right here. So we add this edge to our MST, and then we keep going from there. We want to say, of all of the ranges we can reach, what is the cheapest range? So maybe the cheapest range is between these two still, and this is the only thing that can be reached. So in this case, we remove that range from our list of ranges, and we try and find the next cheapest range, and then we consider adding that edge. So that's the idea. We have a priority queue of all of our ranges. We check, is this range empty? If it's not, like by empty I mean, does this range have any nodes that we haven't already included in this group of nodes which we're growing? We include it if it doesn't have, or if we include one of those nodes, if that node isn't already in our group. After you include a node, you also have to remember anything that node can reach, all of the ranges that node can reach, we need to add those ranges to our priority queue. Yeah, okay, so that's problem D. I didn't show my code for C. It's pretty straightforward. That's the idea. Yeah, you just simulate it for every start node. Cool. Make sure to use print writer so you don't TLE. Okay, yeah, I guess one thing I forgot to mention is to find when the GCD changes, you can binary search that using an RMQ, using an RMQ of GCDs. So that's a fun fact. Okay, I'm not going to explain this code because it's kind of long and kind of annoying. And maybe you can clean it up a bit, but yeah, it's like, 260 lines, including fast scanner, 230 lines without it. So it's very long. I have a bunch of stuff duplicated, right? I have an RMQ for min, an RMQ for GCD. I have a bunch of these binary searches where they're basically just the same thing, copied and pasted with a few changes, right? Like same thing here. So you could probably cut it down to like 150 lines if you needed to, maybe 120. But it's still not super easy to explain. So yeah, I think it's more important to understand the idea and be able to implement it yourself, but actually understanding my implementation is probably not too relevant. Okay, the last problem I want to talk about is problem E. cost equilibrium. So yeah, in this problem, you have like, they explain it in this way, but I'm going to explain it in a way I think makes more sense. You have, well, okay, I guess, yeah, we have to do this. So if I explain it just my way, I make a bunch of assumptions that you wouldn't normally see sometimes. So you have some array. You want to make all of the elements in the array equal to each other. And what you can do is pick two elements, take from one, give to another. Once you've taken from a number, you can't ever give back to it. The cost of taking from one number and giving to another number is equal to the amount that you transfer times the distance in the array that you transfer it. So what you can imagine is you have a bunch of like stacks of stones, maybe. Maybe we're playing like some variant of NIM or whatever. So you have a bunch of stacks of stones like this one, this one. 4 plus 1 is 5. There you go, okay. So what you want is all of these stacks to be the same height, and you can take one stone and move it over by some number, move it over by 2, so it has a cost of 2. And after you do this, you'll have 3 stacks of stones, all height 2. So that's what you're looking for. The first observation here is we know how many stones there are, and we know how many spaces there are. If everything's going to be equal, we know what everything has to be equal to, right? So I thought it was easier if we just say, let's make everything equal to 0 and have some negatives. If we do that, now we have like stones and holes. So in this case, everything is equal to 2, so we have 2 stones, we have a hole of size 1 and a hole of size 1. So we have to put 1 stone in each hole. The question is, okay, the question you finally have to answer is how many permutations of the original array are there so that the minimum cost of putting all of the stones in all the holes is equal to the maximum cost of putting all the stones in all the holes. Yeah. Okay, so I think that makes sense. You can read the statement if you want a bit more details on that. So what are we going to do here? The idea is, let's look at the second sample, because that kind of gives the entire problem away. If you have something like this, right, let's say you have 1 stone here, 1 stone here, 1 hole here, and 1 hole here. If you do this, this would be the minimum cost. You could also have these go in the wrong order. In this case, you have 2 stones across this position. You should have 0 across this position. And you can decrease it by 2 by having these things go to their better positions. So if you ever have like a stone, or if you ever have like a positive and a negative and then a negative and a positive, then this is like an invalid operation, because you can put the positive here and you can put this positive here. Now you've created extra cost, so it's not uniquely defined. So what you need is, if you have multiple positives, then you need all of your positives on one side and all of your negatives on the other side, right? Because you know how many positives will go this way, how many positives will go this way, how many positives will go this way, and also this way and this way. Alternatively, instead of having a bunch of positives and a bunch of negatives, you can have the reverse. You have a bunch of negatives and then a bunch of positives. Now, you don't have to follow this rule in the event that you have only 1 positive, because then this has to go to everyone else. Or if you only have 1 negative, then everyone has to go toward the negative. So it's still uniquely defined. Okay, so after that, the entire problem is just counting, right? It's just some fancy counting. So it's just how many ways are there to do this. You can do that with combinatorics. And there's like one important part that I'll talk about if you're not familiar with it, which like you have to understand in order to be able to solve this, I think. And that is, suppose you have some array. How many ways are there of ordering it? Yeah. So like, let's say you have the array 2, 2, 3, 3, 3, 5, 7. In total, we have 7 positions here. So the question is, how many ways are there of rearranging these elements into unique new arrays? We have 7 positions, So if all of the elements were different, we would have 7 factorial ways of doing this. However, we have 2 2s. So for these 2 2s, there are 2 factorial ways of orienting the 2s. All of those ways would result in the same array. So we need to divide this by 2 factorial. Let's make 4 3s, and then let's get rid of the 7. So the reason we're dividing by 2 factorial isn't because this is a 2, it's because there are 2 of them. Now we have 4 3s. So again, in a similar way, any way of change, like if you give me some array, if you change the order of the 3s, that'll give you the same array still, but it's 2 different permutations. So we need to divide by 4 factorial because you have 4 copies of this 3, and switching any versions of them would create the same array. And then we have 1 5, so we divide by 1 factorial, which is equal to 1, so you don't actually have to do it if you don't want to. And then in total, this will give you the total number of arrays this thing can reach. So yeah, if you have some function that does that, it's pretty easy. If you have 1 positive or 1 negative element, then it's just the number, like you just plug that array into this function. Otherwise, you have a bunch of positives and a bunch of negatives. Plug each of those into this function, and then you solve it there. And then after that, your zeros can be in any positions. So you multiply by the number of zeros, or the number of positions, choose the number of zeros, and choose k. And that's it. That's the solution to this problem. Okay, the last problem I won't really talk about because I don't have a strong idea for it. But basically, the idea is you case out the different things that could happen, right? So if you have 4 possible pairs, there are only 2 pairs that you would actually want to swap. And then for those 2 pairs, like you just do 2 different sweeps to handle each case. I don't have the actual code for it, but I will show you the code for E. So here's the code for E. You store your factorial and factorial inverses, which you pre-compute using fast exponentiation and mod inverse. And then you've got your n choose k from that. After that, you check the count of each number. So you count how many of each number there are once you make everything centered around 0 rather than centered around some other random number. Okay, so we know how many there are of each number. We count how many positive and negatives there are. If either of those are 0, that means the entire array is all zeros, so it's kind of a special case. In that case, the answer is 1, because the array is always going to be all zeros no matter what. Otherwise, if you have 1 positive or 1 negative, you just do that counting way, dividing by the factorials of each count, like I mentioned earlier. Otherwise, you're going to have the positives in the beginning, negatives at the end, times 2, because you can flip everything. And then you put the zeros in at the end. So here's the number of ways of putting the zeros in. This is multiplying by 2. Good. All right. Yeah, that's all. Hope you enjoyed the contest. I thought it was pretty fun. I thought the problems were all good. If you were from India, I hope you got a t-shirt. And if you're in Div 2 and it was rated for you, hope your rating went up. I guess system tests are almost over. I'm not too worried about any of my solutions. I mean, I guess a D time limit exceeded is quite possible. But yeah, I won't make you wait here. Make you wait for the video any longer. So I'm not gonna wait to watch these, because also it doesn't really matter to me too much. Cool. All right. Have a great day. See you in the next one. Goodbye.